let's go ahead and pick up with the end of chapter 6. And I know you got a little bit farther than this on Thursday, but as you might imagine, if I am going to re-emphasize something that you've already learned, it may be very important. So I'm going to re-emphasize something that you've already learned, and it may be very, very important. So the growth of a microorganism and that growth curve are, again, one of those fundamental concepts in microbiology. So a lot like the fact that you should know what the differences are between gram-positive and gram-negative, which was on the previous exam. And remember, I told you it was going to be on there. So I try to be very explicit in what I think is very important for you to know. So I think it's very important that you know and can explain and even draw a fundamental growth curve of bacteria in a culture. When you are growing microorganisms in the lab, they will classically follow this pattern, this classic microbial growth curve, because they are in a closed system. We do not supply them with extra nutrients. We do not remove waste products. They get what they get until they die. That's a closed system. And that is how we get the very classic bacterial growth curve. So again, I would expect that you could draw, label, and explain a growth curve. That literally will be a question probably on the next exam, definitely on the final. So I'm telling you right now, just like I told you about the gram stain or the difference between gram-positive and gram-negative, this curve will come up again. You need to know this. And I know you cover it in the lab, but we cover it here too. So there are 4 steps or 4 phases to growth in a closed system where there is no addition of nutrients and no removal of waste. So of course, we do have exceptions to that classic growth curve. One exception is in an infection. Microbes in the body have access to nutrients. Those nutrients are you. You are the nutrients. And things like lymphatic fluids or blood can take away their waste products. They also have to contend with the immune system or antibiotics. So in an infection, maybe you don't see a classic growth curve, but in a tube you do. So what you have, step 1 is called lag phase. Now, what lag phase means is that the microbes are not actively growing. There really isn't any cell division. There also isn't any cell death. What we're typically seeing here is that microbes are accumulating the nutrients and building the products they need to replicate themselves. Remember, they have to have all of the nucleotides to replicate all of their DNA. They have to have all of the phospholipids to build a whole second membrane. They have to have all of the proteins to fill up a second cell. And when you take a culture that has been, usually we take an overnight culture, it's weak, it's tired. And then you drop it into fresh nutrients, it's not going to start growing right away. So we have that lag phase. Then we have the log phase, or sometimes people call that the exponential growth phase. And this is where you get that doubling, right, every so often. At this point, they are replicating, which is bacterial growth is replication, as quickly as they can. Every species will replicate at a different pace. This log phase will look different in terms of how long it takes for every species. Something like E. coli is pretty quick. In the lab, if you give it all of its nutrients and grow it at the right temperature, it can double every 15 to 20 minutes. We call that the generation time. It takes 15 or 20 minutes for them to replicate. Something like Mycobacterium tuberculosis, you're talking 18 to 24 hours of doubling time. So that log phase can be really expanded because they're super, super slow. So it takes a really long time. Have you done growth curves in the lab? Calculated the generation time yet? Oh, you will. It's a fun one. It's tedious. It's tedious, but you'll do it. So you'll see this in action in the lab as well. Next, what happens in a closed system? So remember, I also like to ask you application questions, not just can you draw the curve, but can you explain what happens in other situations? In a closed system, at some point, the bacteria will have exhausted all of the available nutrients. Does that mean they completely stop growing? Not necessarily. What we see in this phase, which is called stationary phase, is that the overall population does not increase because you have some cells that will start to die. Maybe they're old, there's too much waste buildup, but there will be some continued growth, but it kind of evens out. The number of cells that die and the number of cells that grow are roughly equivalent. In an open system like in us, they may not reach stationary phase because, again, we're a nice, happy source of nutrients. And then finally, there are no more nutrients. They're not really able to scavenge the other cells anymore. They're completely surrounded by waste. Oftentimes, especially with some of your fermentive bacteria, and you'll see this when you do all of the biochemical tests in the lab, when they're in this area or this time of like fermentation, they lower the pH too much. They basically can choke themselves out with acidity. So the metabolic byproducts, bacteria and yeast that do fermentation, they can produce too much ethanol. So there's no more nutrients coming in. There are waste products that are starting to affect the ability to survive. The population decreases. This is the death phase. And we tend to see that the death phase is also logarithmic. It is at a steady clip, that they just keep dying. So again, I will expect you to be able to draw and explain a growth curve, but also to talk about when you might not see a growth curve, like in an infection. So we can measure microbial growth in a handful of ways, and I know Priscilla covered this. I think she said she got to slide like 63. This is 59. So I know she covered this. What you do in the lab, and usually what's most common, is a plate count. So you will do a plate count in the lab. You directly count the number of cells that were living in that culture. The other one that you do in the lab is an indirect measurement called turbidity. There are pros and cons. Turbidity is easy. Plate counts are freaking tedious. That's the one you'll be like, when you're doing it, you'll be like, oh, this is the one she was talking about. Yep, that's the one. That's the one. Okay. So the reason that you would do a plate count, even though it's really annoying, is because it actually allows you to determine the number of viable cells. How many living cells are in here? And when you're doing that, you would plot it out at time 1, time 2, 3, 4, 5, 6, 7, 8. Right? And you would get that curve. But again, it is tedious. It can be a little bit error prone, especially if you're not, experienced with things like pipetting and doing the small volumes. And plus, in the lab, we give you that weird bulby thing to do pipetting. I'm like, just give them a regular pipette, but that's okay. So, you can make mistakes. And then, you have to do all of these dilutions. You have to plate out the dilutions. And then you have to physically count the number of colonies that grow on a plate. You'll do a little bit of math. By factors of 10, you'll do a little bit of math and calculate the number of cells per milliliter that were in your original culture. And again, you could plot it out and get a growth curve. The assumption, of course, being that a single colony arose from a single cell that was in the original mixture. You can do plate counts a couple of different ways. In the lab, you will typically do a spread plate. So the plate is already made. You take a liquid culture, put it on top, and then spread it around. We call it the hockey puck, but it looks like a hockey stick, and you just spread it around. You can also pour a known volume into your auger as you're making the plate. This one's a little bit tricky because if you pour when the auger is too hot, you fry the bacteria. If you pour when the auger is too cold, it's all chunky and weird and you don't get a nice plate. So I prefer, personally, I do a spread plate when I have to count. You can also do membrane filtration. This would be something that might be applicable if you have a low concentration of cells. Because if you're filtering something that is dense in cells, like for example, a culture of E. coli in 1 milliliter could have, 1 trillion cells in 1 milliliter. How are you going to count 1 trillion cells, right? You filter a liter, you've got more cells than you know what to do with. But sometimes in water, you might have far fewer cells, especially if it's like your drinking water, because later you'll bring in a sample of your own water. And you have to filter it to see if you can collect any bacteria. So you filter a large volume, you can put the filter on a plate and see what grows. What you do in the lab is you look for fecal bacteria. So there might be other bacteria that are in there, but only the fecal bacteria will grow. Man, the look on their face when it's like the Brita filter and it grows all this fecal bacteria, I'm like, yo, you gotta clean your Brita filter. Okay. This is also used in water testing. It's the most probable number. They say it's direct count, but I don't think it is. I think it is more of an indirect count. But again, it just involves using different ratios of cells and looking for growth because of fermentation. So this is, again, really common in water testing. So, a lot of biotech related jobs that people in the Valley get are at food and beverage facilities. So these are types of things that you might do. Like winemaking is huge. The water treatment facilities, any sort of food production, they all hire microbiologists. And these are the types of assays you do. Also very tedious, maybe even more tedious than counting on a plate, is counting under the microscope. How much do you guys like looking at the microscope and trying to find your bacteria? Not a lot. How much would you like to have to sit there and count all of the individual cells? Even less, right? So you can directly count the cells. Typically, we don't. Those of you who maybe are considering careers in clinical lab science, you will spend a lot of time looking down a microscope. Usually you'll be counting immune cells rather than bacterial cells. So you'll count cells, but counting bacterial cells is tough. And again, one of the things here to point out, this does not distinguish between living and dead cells. If you look at a bacteria under a microscope, do you know if it's alive or dead? What if it's a non-motile species? How do you know? Just sitting there. Is it alive or dead? Don't know. So again, I don't like this as being called a direct measurement because you can't tell which ones are alive or dead. So technically, I think the best is the spread plate, the plate count. Okay, indirect, which you'll do in the lab, is turbidity. What you're looking at is an increase in how cloudy the culture looks, and that's because you'll have bacteria that are blocking the transmission of light. But again, if you can't tell the difference between a live and a dead bacterial cell under the microscope, a spectrophotometer can't tell the difference between a live and dead one that's blocking the light. Dead bacteria block the light just as well as live bacteria. Okay. So sometimes what can happen is when you try to plate out turbidity measurements, you'll see, right, the classic growth curve, but then it just kind of does something like this. Because you've got all the dead cells in there. So you don't get the classic really nice growth curve that you get when you do live. Eventually though, they'll explode and you'll get, the decline. It just takes longer. But it's much easier. You just put a little culture in there, you put it in the machine says 0.5, write down 0.5, you're done. Much easier than counting. And again, I've never done either of, well, no, I haven't done these to estimate bacterial number, but theoretically you can. I know people who've done this to like measure the amount of carbon dioxide produced by bacteria or the amount of oxygen consumed. So you can kind of extrapolate based on metabolic activity how many microbes might be in a particular area. Or you can like filter them, dry them, and weigh them. It seems too much for me. So there are lots of ways, but I think probably the two most important ways for you to understand for measuring microbial growth are going to be the spread plate, right? That you actually are physically counting the number of cells on the plate, which is a really great measurement for getting the viable cell count, the number of living cells. And then turbidity, just because it's fast, and especially in lag and log phase, turbidity and plate count are really highly correlated. Stationary and death phase get a little bit weird when you start to do the plate count and turbidity correlations, but lag and log, really solid. So again, plate counts and turbidity are going to be your two most common ways to measure the number of microbes. Okay. Questions, comments, concerns about microbial growth before we move on to let's stop microbial growth. We know how they grow, let's figure out how to stop them. Okay, let's figure out how to stop them. Chapter 7. This is a very important chapter for those of you interested in things like healthcare, right? We want to stop microbes from growing. Okay, so why? Why do we want to stop microbes from growing? Well, I'm sure you can imagine why. There are lots of reasons we would want to stop microbes from growing. In every environment, absolutely not. In some environments, definitely. We want to stop, really importantly, infection. I don't like being sick. Not my favorite. Food spoilage. I think we had this conversation like first or second week of class. You don't want to eat the moldy strawberries. If you do, no shame. I mean, that's on you. But most of us would prefer, right, to not eat food that has been spoiled. And we don't want to eat things that are contaminated. You don't want to drink water that has fecal bacteria in it. So we want to control microbial growth for a number of different reasons. So we'll talk about sepsis, which is microbial contamination. Asepsis, which is the absence of significant contamination, but look, it's not sterile. The absence of significant contamination. And aseptic surgery techniques. Prevention of contamination of wounds. And of course, that's very important. You can have people who are 100% healthy that have to go in for surgery and they can get a surgical infection and die. Any 49ers fans? Anybody 49ers fans? Alex Smith, you know? His leg. Yeah, so I mean, an NFL quarterback, they're fast, they're healthy, they're not like the big guys that stand in the front. And he broke his leg during a football game, a compound fracture, so he had an open wound. And it got so infected, they almost amputated his leg. So, you can have that happen. I had a student in a class I taught my first semester who did a presentation on a bacterium, and they had to do like a brochure or whatever, and there was a picture of a infected wound, and I'm like, oh my God, that better not be her body. It was. She'd had back surgery, and every single person that had been operated on by that surgeon over a 2-day period got Pseudomonas infections in their wounds. I had to put a disclaimer the next time I taught the class. Please do not put your own wounds in the thing. But yeah, it was her own wound. I was like, oh, she's gonna do it. Yeah, she did it. Okay, but like, you go in for a surgery and you come out with an infection that, I mean, if you look at Alex Smith's leg, it looks terrible. It's all like missing tissue and stuff. But at least he's alive. And that's not what we can say for everybody. So it's really important that we have that concern. So the type of control of microbial growth that we want to do really depends on the situation. What is the goal here? Obviously, you would expect probably the strictest protocols when it comes to something like surgery and hospitals. You want those individuals who are vulnerable to be as protected as possible. And the amount of contamination or microbial growth that is tolerated may increase, when we decrease in the severity of the situation. So in daily life, what do we do to control microbial growth? Hopefully we bathe. I say hopefully, I don't know. Right? Brush your teeth. Wash your hands when you leave the restroom. I mean, but we've all been in there when somebody didn't. You're like, I heard the flush and then the door. Mm-hmm. Okay. We don't cough and sneeze in front of other people. We wash our clothing, our bedding, often with things like soaps or detergent to mechanically, physically remove microbes. You just wash your hands. Usually your beneficial skin microbiome is not going to be harmed by you took a couple of showers. You washed your hands after you went to the bathroom, right? Your oral microbiome is not going to be harmed because you flossed and brushed your teeth twice a day. But hand washing with soap and water is the most important step in stopping the spread of infectious disease. Like the microbiologist in me, how appalled I was every time I go to Target, there was no toilet paper, but there was a ton of soap. And I'm like, y'all, why is there so much soap and there is no toilet paper? People with carts full of toilet paper and no soap. I'm like, y'all, that's gross. Okay? Do you need to wear, the guy at Whole Foods, like with the gloves, I'm like, you don't need to wear gloves when you're pushing the shopping cart. Do you lick the shopping cart? No. Right? Do you wash your hands after you're done pushing the shopping cart? Yeah. Managed to take toddlers to Disneyland and nobody got sick because we just stop and wash our hands. It's not that hard, okay? So that's kind of what you do every day. And you don't necessarily maybe think about it as I'm removing microbes, but you think of it as I'm getting clean. But that's what getting clean is. You're removing any microbes that could potentially be harmful. Now in hospitals, of course, this is far more stringent, and this is really life or death. If you decide that you want to go to the bathroom and not wash your hands, you're nasty, but that's on you. Don't make my food. That's why I don't like to go out to eat. I don't trust you. But it's kind of on you. If you're in the hospital and you have a big open wound because you've just had surgery, or you have another infection that's already put you in the hospital, or you have cancer, or whatever, you're in the hospital, there is something wrong. You don't go to the hospital for funsies. You are far more susceptible to infection, no matter the reason. You tore your ACL, right? Because you're a soccer player, you're super athletic, but you tore your ACL. You are probably one of the healthiest people because all you do is run all the time. But they're going to cut open your leg, which means that you could get an infection. So those invasive procedures, actually some of the worst are burn wounds. So patients that have burn wounds are really susceptible to infection. And they tend to have worse infection than patients who have like surgical or cutting wounds. So those instruments, they're not just antiseptic, those need to be sterilized before they're used. And, the cleaning protocols in the operating room are absolutely critical. Because one of the other challenges is that when we do find pathogens in the hospital, and we do, they are more often resistant to antibiotics, which is what we'll talk about in the next chapter, chapter 20, because we're going to go from 7 to 20. I think they tie together nicely. Okay. But, you would be surprised at where in hospital settings you find antibiotic-resistant microbes. In the plumbing, in the soap dispensers, in the ventilation. So it's absolutely critical that as much as possible you are being protected if you are the patient in the hospital. And of course, we can't forget how important it is for you as the healthcare professional to stay healthy. That was one of the major issues during COVID, is the healthcare professionals were getting sick and not able to work. So having that protection, right, of course, as the healthcare professional, like your goal is to protect your patient, but you can't forget yourself. So you have to think about all of that in the context. And if anybody visiting, in microbiology labs, those of you who are going to be in clinical lab science, of course, you have to use aseptic technique. You don't want to contaminate a patient's sample, so you make a wrong ID of the infection, or that you make yourself sick from a patient sample. So you have to consider all of those things. And what we do in the lab to protect you is when we give you media to grow microorganisms in, we make sure that it is sterile first. So there's nothing growing in it. It is already sterile. Once you have grown something, we sterilize it again so that we don't contaminate the campus, we don't contaminate the environment, custodial staff are not at risk, and you aren't at risk the next time you come into the lab. So it's just really, really important that we control microbial growth. And now when we talk about different levels of control, sterilization is usually the goal when we are talking about instruments that will go inside somebody's body, when we are talking about having media that we can use for growing microorganisms, and when we are done growing microorganisms, to get rid of those microorganisms. So by saying the term sterilization, what you are saying is that you have destroyed all microorganisms, including endospores, including viruses. There are no microorganisms left. You cannot sterilize a person. So you don't sterilize a patient's wound, but you sterilize the equipment that might be used on that patient. Even if you're going into dentistry, right? Somebody's going to put some tools in your mouth. Those better be sterilized because they were in somebody else's mouth. It's gross. I know. If you go to a tattoo parlor, those needles, That machine better be sterile. You go to a piercing studio, that needle better be sterile. So places like that, even nail salons, they're clipping your nails and filing your feet. That nail file touched somebody else, it better be sterile. A lot of those places will have their own autoclave to sterilize the equipment, not just clean it.
I have gone to a salon where they faked the autoclave and the marks were not on the table.
And did you leave? Yeah, okay, good. Yeah. You should be able to see them open the pouch, and all autoclave pouches will have a color indicator. So if you don't see a color change, leave. Pedicure's not worth it, promise. The piercing isn't worth it, the tattoo's not worth it. Leave. They should open it right in front of you. That's really gross. What nail salon? Name and shame. Oh, okay. Well.
It's in San Diego.
Oh, okay. Okay, we're fair. That's fair. Commercial sterilization, and this is usually in food production. We don't sterilize all of our food, but we do sterilize our canned goods. And the goal of sterilization, especially with the canned goods, is to remove Clostridium botulinum endospores. So Clostridium is a gram-positive genus of bacteria. They are anaerobic. So they will be spores if exposed to oxygen, but once you seal them up in a can and you remove the oxygen, they can germinate. And the problem is when they germinate, they make a toxin, botulinum toxin. And that toxin can kill you. It's one of the most potent toxins that we know of, at least naturally occurring. So if you ever see like a bulging can at a grocery store, don't do it. If you're a jelly jar, it's already like the pop is, you open it, it doesn't pop, that's a problem. It needs to pop. We typically see this in home canning. So people who do their own canning. There was a case in Fresno maybe a year and a half ago where they were, somebody was canning their own nopales. And I think like 9 of the family members got botulism. And they all ended up surviving, but you know. And sorry if you're one of these folks, because I used to be, but now I'm not. If you eat gas station nachos, there was a case in Sacramento where like a bunch of people got botulism from the gas station nacho cheese and one guy died. So it's really important that we have that sterilization at the commercial level, right? I'm like, maybe I expect indigestion or food poisoning from gas station nachos, but not like botulism. Okay. Of course, people will willingly pay to inject botulism toxin in their faces, but it's Botox. So I don't pay. Obviously, I don't pay, but people pay. Okay. So that's sterilization. You're getting rid of everything. Nothing should be living. No life, no viruses, dead, everything. Next is disinfection. So disinfection is classically what we do kind of on the daily. You use things like pine sol or, whatever, diluted bleach, whatever you use maybe to clean your restroom, clean your kitchen surfaces, the Roll-Call you put on the surface of the lab bench. These are disinfectants. They're used on inanimate objects and surfaces, but the goal is not sterilization. The goal is the removal of as much contamination as possible to reduce the risk of the growth of unwanted microorganisms. When I took micro as a student here, Dr. Tao had us go around and sample areas in the building. And of course, everybody beelines to the bathroom. They're like, let me, swab the toilet, see how nasty it is. They clean the toilets every day. It's not the toilets, it's the door handle. Okay? Because, people don't think. When was the last time, at your house, you thought to clean a door handle? Okay. Even in your bathroom. Oh, yeah. It's gross. If you have roommates, I hope you don't keep your toothbrush out in the bathroom. That stuff, flies from the toilet if you don't put the lid down. Okay. Antiseptics. Mine is like very far away from the toilet in a drawer. Yeah. Antiseptics are what we use on living tissue. Now, sometimes you can have the same chemical, even at the same concentration, and you can use it as a disinfectant or an antiseptic. It just depends on the use. For example, the active ingredient in this hand sanitizer is 70% ethanol. That's basically the same thing that you could spray on a lab bench to disinfect it, but I could also put it on my hand as an antiseptic. Sometimes a chemical that is used both as a disinfectant and antiseptic may be at a different concentration. You might use a higher concentration on an inanimate object, whereas if you use that same concentration on your skin, maybe it would cause a chemical burn or something like that. Mouthwash is an antiseptic, right? So things like that. Okay, this is the one that always grosses me out too. Running things through the dishwasher, not as good as you might expect at removing microorganisms. So we call that sanitizing. I mean, let's be real. You've all gone out to eat and they bring you the silverware, right? And it's not clean. They bring you the glass and you're like, I could see that person's lip print. Right? This is why I don't like to go out to eat. People are gross. I trust no one, okay? But you're just lowering, not eliminating, lowering the microbial counts on eating utensils. And especially in commercial kitchens where they're like, well, we've just had 100 people. Here are all of the plates. Let's just shove them in the dishwasher. It's probably not as effective as your dishwasher where you put in like 5 or 6 plates, there's enough space, everything's good. That's not how it works in a commercial kitchen. Okay, so that's what you do to stuff, sometimes food, maybe you. Then there's what we can do for beverage products, things you want to drink. We can pasteurize them. So the idea, again, behind pasteurization, you'll notice I don't say sterilization. Anything that has been pasteurized is not going to be sterile. But the goal behind pasteurization is to briefly heat. And when we talk more about pasteurization, it's literally like 30 seconds or 15 seconds at ultra high temperatures to hopefully destroy as many organisms as possible that would cause that beverage to spoil. Right? I think at some point, probably all of us have grabbed the milk and been like, oh, I regret this. Do a little taste test and whoops. It's not, it's not pathogens. It's just the bacteria that grew in there and made the milk chunky. Like I wasn't trying to make cottage cheese, just wanted to drink my milk. Or orange juice. I don't know, something about spoiled orange juice that really is just foul. Okay? And hopefully destroy pathogens. So again, just because your milk is chunky doesn't mean it's pathogens. It's just the food spoilage microorganisms. They produce a lot of acid, that's why it tastes bad. And we can try to preserve and control microbial growth. And we typically do this with our perishable products, often food, but also medicines, medications. Various vaccines have to be transported under like refrigeration. Sometimes you'll get a drug at the pharmacy and they'll tell you, hey, this, you got to put it in your fridge right away. But of course, a lot of our food and beverage products, we put them in the refrigerator to help preserve them. Like, I think we're all aware of the idea that no matter what type of produce you get, it's not sterile. There are going to be microbes all over it. So you put it in your refrigerator to help preserve it as long as possible. So you can adjust the storage conditions. Again, refrigeration or freezing, depending on the product. Or for some of our products that are at room temperature, we add preservatives. So a lot of, bread, for example, has a lot of preservatives in it. unless you buy the kind that says no preservatives, and then it gets moldy in a few days. Or you get the one that has preservatives and it stays on your shelf for like a month and a half, and you're like,
So for people who live in like third world countries that don't have like all this available, is their immune system just like stronger, or is there?
the leading cause of death in children around the world is diarrhea. Because they don't have access to uncontaminated products. They tend to have really high levels of things like parasite infections, things that we don't typically see here. That's one of the biggest challenges in delivering vaccines to certain parts of the world, is because there's no refrigeration, there's no preservative, there's no way to keep it stable for the ones that have to be refrigerated. Yeah. So unfortunately, it's not necessarily that they have a stronger immune system. Sometimes people adapt, right, and can tolerate, it's kind of the idea of maybe people who live in a country where there's not great water control in all places. They can drink the tap water and be fine, but we go there and that's right, very unpleasant. But yeah, in developing countries, the leading cause of death in children under the age of 5 is diarrhea. So it's a big problem. And, the idea that we have this ability to have food that's free from contamination, but especially water that's free from contamination, you tend to see that as soon as a country is able to get a stable enough infrastructure to provide clean water, the economy just whoosh. And that's why one of the first things that they'll do, like when they're having conflict, is you go after the infrastructure. You make everybody sick. Yeah. So, there's a lot of, I know this is like a science class, it's microbiology, but it has a lot of impact in other fields as well. So when we talk about compounds or antibiotics or really anything that has an effect against microbes, we use a couple of different endings. We can talk about it ending in "ide" or "cidal." This means that it kills. A biocide, a germicide, bactericide, fungicide, it kills. If it kills by lysing, kills by exploding the cell, that would be bacteriolytic or cytolytic. So sometimes we want to kill. Sometimes it's just okay if we can inhibit the growth. So if we inhibit the growth without killing, we say it's static, like bacteriostatic. And broadly, when we are talking about controlling microbial growth, especially to either inhibit their ability to reproduce or to directly kill them, we have 3 broad targets. 1, we alter the membrane. That one will usually kill. If you change the membrane enough, they will probably die. 2, you damage proteins. Often enzymes, that's why heat works so well, because it denatures the proteins. That's why acids and bases work really well, because they denature the proteins. Or you can damage the nucleic acids. That's what UV light does. It causes mutations in the DNA, which eventually will prevent the microbes from reproducing. So again, broadly, we're affecting the cell membrane or cell wall, proteins, or nucleic acids. Those are the big targets when we're controlling microbial growth. And like we saw on, not this one, that's the bad one. On this one, the normal growth curve, bacterial populations do tend to die in a logarithmic rate. That's just kind of a constant rate. We don't see a start and stop of the death. Once they start dying, they die. But now, how quickly death occurs can depend on a number of different things. If you have a really low population, as they die, right, pretty quickly they can get to 0. When you have a larger population, it just takes longer. So the more contaminated a surface might be, the longer you would want to expose it to the cleaning product. I don't know if you like actually look at the labels on your cleaning products at your house, but a lot of them will say that you need to leave it on the surface for like minutes, not just like you have to let it soak in there to actually affect the microbes. It's, you know, it sucks. It sucks to know all this stuff and be like, oh, everything's contaminated. But it also depends on the environment. If something is growing in organic material, perhaps the growth rate or the death rate would be affected, depending on what the temperature is, right? Higher temperature, you might get a faster curve. If they formed a biofilm, that makes it really tricky to get rid of things. So that could extend the time to death of the population. The time of exposure, right? More time is required for more resistant bacteria. That's the part that always freaks me out in like the Lysol commercials. Gets rid of 99.9% of germs. I'm like, yeah, but that 0.1% that you left behind is now going to be what's growing. What do I know? I don't think it's great marketing, but that's just me. And of course, the characteristics of the organism, gram-positive versus gram-negative, endospore versus not. All of that can play a role. But not just thinking about the characteristics of like only bacteria. What about the characteristics of it as an organism? Not every organism is equally susceptible to a type of treatment. Classically, we talk about endospores as being like, ooh, right? Hardest to get rid of. Actually, the hardest to get rid of are prions, like mad cow disease. If you use a standard autoclave protocol to try to inactivate prions, it will fail. It will get rid of endospores, it will not get rid of prions. So prions, most resistant to heat, most resistant to different kinds of chemicals. You can get rid of them, but it's the biggest challenge. Then endospores. Then your mycobacteria. So remember, mycobacteria, like Mycobacterium tuberculosis, have mycolic acids in the cell wall. That provides them a lot of environmental stability, keeps them from drying out as much, protects them from a lot of antimicrobial compounds. Then you have protozoans that form cysts. So some of our unicellular eukaryotes, like Giardia, will form a cyst that can persist in water for an extended period of time until you drink the water and then it germinates. So they're pretty resistant. But you know, once we get to endospores, right, autoclaving is going to get rid of them. Cysts of protozoan, like filtering, boiling your water, it won't tolerate all of that. Like if you ever watch shows like Naked and Afraid or Alone and you're like, dude, boil the water before you drink it. You watch them drink it, you're like, Okay, boiling it, you're fine. Vegetative protozoa, so like an active replicating protozoan cell. Then your gram-negatives, the LPS is what helps protect them. Then your fungi. Then your viruses without an envelope. It's gonna be something like norovirus. So they don't have an envelope, so it helps them be more resistant to things like drying, so they won't like dry out on a surface very well. Then gram-positive bacteria, they only have they have like the one membrane, the cell wall. Once that cell wall falls apart. And then the weakest are actually your viruses with envelopes, which is why I'm like, how does flu and how does COVID like spread? They have envelopes. Literally wash your hands. So we know that people don't wash their hands. These are the most sensitive. They're sensitive to drying. They're sensitive to chemicals. They're sensitive to temperature. They're sensitive to soap. They're very sensitive. So the type of control that you might think about for any particular environment really depends on what is the risk factor. And we can use physical methods of control, so things like heat, filtration, or radiation, or we could use some kind of chemical, or maybe we use both. But there are a number of different ways that we control microbial growth. And of course, really, really, really commonly we talk about heat. We use this in our homes, right, to control or to get rid of microbial growth on food. We use it in the lab, right? You put your loop in the flame. But again, what you have to think about is what is the temperature required to kill bacteria? That's why they tell you you have to heat your chicken to whatever temperature and your beef to whatever temperature, your fish to whatever temperature. I don't really eat those things, so I don't know. Which is good. You never trust like a vegetarian to make you meat. Like, I don't know. If you don't hit the right temperature, that's why undercooked hamburgers are going to make you sick. It's like roulette. At some point, you're going to get E. coli. It's going to happen because you didn't cook it all the way through. Not steak. Steak is tapeworms. Hamburgers are E. coli. Chicken is salmonella. Raw eggs, salmonella. That's what's going to happen. Okay? So you have to think about what is the temperature you actually need to achieve the reduction in microbial growth you want. If there are some E. coli in your hamburger, are you going to get sick? Probably not. If there are lots of E. coli in your hamburger, it's a numbers game. So you think of what is the thermal death point? At what temperature, what is the minimum temperature if I maintain this at this minimum temperature for 10 minutes, at what point can I get rid of all the microorganisms? That's the thermal death point. You could also talk about the thermal death time. How long do I have to leave the cells in a culture at a particular temperature? If I hold it at 65, that thermal death time is probably going to be a lot longer than if I had it at boiling. So the time it takes to kill everybody changes with the temperature. That's your thermal death time. But often, I mean, again, you don't have to kill all of the organisms. You really don't. We eat, we inhale, we drink microorganisms every day. And you're all here. You all look healthy. Maybe tired, but healthy. It's okay. So, what about the decimal reduction time? What if we just can reduce the microbial population enough that we can handle it? So, the minutes to kill 90% of a population at a given temperature. 90% reduction is pretty good. I mean, you know, if you're starting with 1 million cells, 90% reduction gets you down to 100,000. I'm not comfortable with that. Maybe I get it down to 10,000, so another 90% reduction. A lot of foodborne bacterial illnesses, you have to consume 100,000 or more bacteria to make you sick. At 10,000, I got this. Okay. So 10,000, maybe that's okay. Maybe it's 1,000 or 100 or 10 or 1. That's where you want to be with norovirus. It only takes 10 norovirus particles to make you sick. So you want to be down to 1. So it depends on the organism, like how much you need to go down. But that decimal reduction time is reducing the population by 90%. And again, like sometimes that's good enough. Most of the time, that's good enough. Right? We have things like enzymes in our saliva that can break down microorganisms. We have acid in our stomach that can break down microorganisms. We have a whole community of other bacteria in our gut that are like, no, this is our spot, you can't play with us. So just reducing enough, doesn't have to be sterile, doesn't have to be down to nothing, can make a lot of our products safe. And when we talk about heat, we can talk about the difference between moist heat and dry heat. And moist heat is better. It allows better penetration of the heat into the cell to denature a lot of those internal proteins. Boiling is awesome. Almost any use that you would need to reduce microorganisms, if you boil, you're going to be great. If you go camping, boil. I mean, it's very unlikely you would get botulism on the trail. Giardia? Or whatever else. Bears leaving the water. When we get to tapeworms, you'll see why I said bears. Okay, boiling, right? But we use the autoclave. So what's the difference between an autoclave and boiling? They're both moist heat, but the autoclave uses pressure as well. So it raises the pressure to 15 psi. The temperature in there goes up to 121, so even hotter than boiling. The pressure, the heat, for 20 minutes is sufficient to get rid of endospores. So that's all you need, a 20-minute cycle on an autoclave. For prions, it's closer to like 2 hours. But it can be done. And so we were talking about this idea of there will be some sort of test strip. Usually if it hasn't been autoclaved, it's going to be clear or kind of this yellowish background, beige color. If it has been successfully autoclaved, it reached the right pressure and temperature for the right amount of time, it changes to a darker color. And periodically, autoclaves need to be tested. We test them by putting in packets of endospores. And if we can grow them afterwards, that was bad. If we can't, we know the autoclave is good. So autoclaves can be very big. We have really large ones, but they can be a tabletop size. So again, those of you who might have your own dental practice, or hey, you're an artist, you go into tattooing or piercing or whatever you want to do. Little autoclave, buy one, good investment. You want to open a nail salon, get one, and please use it. Pasteurization is a similar principle. We're using moist heat, but we do it very quickly because, as you might imagine, if you boiled orange juice for an extended period of time and then tried to cool it down and sell it to somebody, it probably wouldn't taste all that good. Or milk, right? You want milk that somebody's boiled and repackaged for you. Okay. Would it hurt you? No. Will it taste good? Mm-mm. So what pasteurization has to deal with is this idea that you have to get rid of organisms that can cause spoilage or pathogens and preserve the appearance and taste of the product. You're gonna buy orange juice that's not orange? What's wrong with this orange juice? No pulp, but there's all this chunky stuff in it. You're not gonna buy it. So how do you balance that? When you have to get rid of spoilage organisms, and the most effective way to do that is heat, filtration would be too expensive. But you don't want to boil the food. You do quick heat. So this is not quick, 63 degrees at 30 minutes. You almost certainly would not want to consume this beverage that had been processed this way. But 72 degrees for 15 seconds is as effective as 63 degrees for 30 minutes, which is as effective as 140 degrees for 4 seconds. So this ultra high temperature, really fast pasteurization reduces spoilage organisms, reduces pathogens, and makes beverages like milk more shelf stable and safer to drink. But again, organisms that are thermoduric, they can tolerate high temperatures, or endospores might survive. But the majority of organisms that cause food spoilage or cause pathogenesis in people are not thermoduric and mostly don't have endospores. So this works really well for us to keep us safe from our food. We'll pick up on Thursday with dry heat sterilization. And as always, if you have any